Hi everybody. This is our lecture on section 4.7, maximum and minimum values of functions. Two variable functions. Given, or suppose that z equal to fxy is smooth and continuous. It's a surface that is smooth and continuous, meaning that fx and fy, the partial derivatives, fx and fy, exist at all x and y. Okay, so the surface always has its partial derivatives, always has its tangent planes. Okay, if fxab equals fyab equals 0, then AB is called a critical point for fxy, and the tangent plane to z equal to fxy at the point AB, FAB, is horizontal. So we have one of the following pictures. So a horizontal tangent plane might happen like at a spot like this, which is a relative maximum. So this slope is 0 in the x direction, 0 in the y direction, so, or that's fx is 0, fy, or no, this is the x direction, fx is 0, fy is 0, and this is a relative maximum. All right, or you could have sort of the opposite picture to that. See if I can draw that. Right, so yeah, these lines going up are nice as well. So this would be a relative minimum. Fy equals 0. Fx equals 0, relative minimum for the function. So that's the surface z equal to fxy. This is the surface z equal to fxy, and that's relative minimum, relative maximum. But it doesn't have to be either or. You can have these saddle points as well. So here in this picture, this would be fx, and it's equal to 0. this would be Fy here, and that's equal to 0. Come on. And so the tangent plane is horizontal there as well. All right, and this is neither a relative max or min. Neither a relative max nor a min. All right, how can you tell the difference? Is there a way to tell the difference? Well, not always. Sometimes yes, sometimes no. But in general, you can't always tell. Okay, this is called the second derivative test. And it says the following. If AB is a critical point for fxy, let D equal fxx, fyy minus fxy squared. So you take these second partial derivatives, and then you just let D be equal to this thing here. It's called a determinant, and it's it's like a 2x2 determinant. It's fxx, fyy, fxy, fyx. But fxy and fyx are supposed to be the same thing, as long as you have a nice, continuous, smooth surface. Okay? So that's a 2x2 determinant. If D is greater than 0 and fxx is bigger than 0, then AB is a local min. If D is bigger than 0 and fxx is less than 0, then AB is a local max. If D is less than 0, then AB is neither a local max nor min. And then if D is equal to 0, then the test is inconclusive. Okay? So unfortunately, you have this situation in which it's inconclusive, and that can happen all the time. So, for example, if I have the function z equal to x squared plus y squared, right? That's that paraboloid. Right? There's only one critical point there, and that's at 0, 0. Right? We know that. We know that this is what the surface looks like. What did I do? Hold on. There we go. All right, so the surface looks like this, and clearly there is only one critical point. right, where the tangent plane is going to be horizontal, and that's at 0, 0. Okay, well, let's check it out. The partial derivative of z with respect to x is 2x, and the partial derivative of z with respect to y is 2y, and you set those both equal to 0. Well, this implies x is equal to 0. This implies y is equal to 0. So 0, 0 is the only critical point. All right, now let's try the second derivative test. Now zxx is 2, zyy is 2, and zxy is 0. So d, which is zxx, zyy, zxx times zyy minus zxy squared is just equal to 4, which is positive. And zxx is positive. Right, so 0, 0 is a local minimum for z equal to x squared plus y squared. Right, it's actually a global minimum, but we see that it's a local minimum there. How about the following? Something where we don't know. Where the critical points are. So let's look at fxy equal to xy minus 1 over x minus 1 over y. Find critical points and determine if it's max, min, or neither. If each is a relative max, min, or neither. If you can. Well, the partial derivative of f with respect to x. Well, here, the partial derivative of f with respect to x is just y. The partial derivative of f with respect to x here is minus 1 over x squared. And this one is 0. And then we set that equal to 0. And the partial derivative of f with respect to y is x minus 0 plus 1 over y squared. And we set that equal to 0. Okay, so we have oh, I want to make this plus. So then this is minus. There we go. So we have these partial derivatives. So now we have to solve. But this is one equation with two unknowns. So you can't solve for x and y here specifically. But now we have a second equation with the same two unknowns. So two equations with two unknowns. Hopefully we can find a solution. All right, given that y is minus 1 over x squared is 0, y is equal to 1 over x squared. So now x minus 1 over y squared equal to 0 becomes what? Y is equal to 1 over x squared. So this is x minus 1 over x squared squared. So I took the first equation. The first equation tells me y is equal to 1 over x squared. So then I took this y and stuck it in there. And I get x minus 1 over x squared is 0. So this is x minus x to the 4th is 0. So I have x times 1 minus x to the third is 0. And, what are the solutions here to this polynomial equation? So this tells me that x is equal to 0, or x to the third is equal to 1. Right? X is 0, x to the third equals 1. So this gives me x equal to 0, or x equal to 1. The only real number solution to x to the third equals 1 is just x equal to 1. Not even negative 1, right? Because negative 1 to the third is negative 1. There are two other solutions, but they're imaginary solutions. All right, so the critical points happen when x is equal to 0 or x is equal to 1. Now we just got to find the y's that go along with it. Right? They happen when x is 0 or x is 1. It's a little messy here. Come on. So now find the y values corresponding to the two x values. All right, so for x equal to 0, okay, for x equal to 0, this is going to give me 0 is equal to 1 over y squared. Or 0 minus 1 over y squared is equal to 0. So no solution. Right? We can't say y is equal to 0. 1 over 0 is undefined. So no solution here. And then if x is equal to 1, right, we've got 1 minus 1 over y squared is equal to 0. Right? So y squared is equal to 1. So y is equal to plus 1 or minus 1. Right? So the critical points, hold on a second. I think maybe, yeah, with this one it just gives you y equal to 1. So this one gives you two solutions. Right? There's two equations to pick. There's y minus 1 over x squared is 0 and x minus 1 over y squared equal to 0. And you plug in x equal to 1 into both of them. Unfortunately, that one gave you two solutions, but you have to solve both of them simultaneously. Right? So let's do them both simultaneously. Y minus 1 over x squared is equal to 0, and x minus 1 over y squared equal to 0. Here, if you plug in x equal to 1, so 1 is equal to y squared, so plus or minus 1 is equal to y. Here, y is equal to, y is just equal to 1. Right, so the only solution simultaneously to both is x equal to 1, y equal to 1. X equal to 1, y equal to negative 1 doesn't solve both equations. The only critical point is x, y equal to 1, 1. So now, is that a relative max, relative min, or neither? So let's go to the second derivative test. So looking at the second partial derivatives, right, zx was equal to what? Y minus 1 over x squared, and zy was equal to x minus 1 over y squared. So now zxx is minus 2 over x to the third. Zyy is equal to minus 2 over y to the third. And then zxy, the derivative of this with regard to y, is just 1. So at the given critical point, 1, 1. So zx11 is minus 2. Zyy at 1, 1 is minus 2. And zxy at 1, 1 is just 1. So d, which is equal to zxx zyy minus zxy squared is equal to 4 minus 1, which is 3, which is positive. And zxx is less than 0, right? So 1, 1 is a relative max for z equal to x, what was it? X plus, I forgot what the original function was, xy plus 1 over x plus 1 over y. But there, again, like I was saying, there are functions where you don't get an answer, where this second derivative test is inconclusive. So, for example, z equal to x to the fourth plus y to the fourth has a critical point at 0, 0, but calculating d at 0, 0 yields just d equal to 0. So it would be inconclusive there. Now, this function, it looks a lot like the paraboloid. It's just kind of more, it grows faster, so to speak. Right, so we see that critical point is a local minimum for the function, but calculating that d just gives you d equal to 0. Okay, so the d is not the best solution in the world, but that's just one way to tell. All right. So what were these maximum and minimum values of functions used for back in Calculus 1? They're used for, applying to a variety of situations, these applied maximum and minimum problems. So let's take a couple examples of those. Now, with applied max and min problems, you shouldn't have to use this d. Okay, you should know whether the critical points that you get, well, you won't always, but sometimes you'll know. If you only get one critical point and you're looking to maximize a function, you know it's relative max. It's a global max. If you're looking, if you only get one critical value and you're looking to minimize a function, then you know it's going to be a global minimum, as long as the problem is defined correctly, which I will always give you. So let's start with one, a very standard example. So a rectangular box with an open top is to be made from two sheets of two kinds of steel. Okay, the bottom uses steel costing $8 square foot. And the sides use steel costing like $5 a square foot. And so using slightly thicker steel on the bottom or something like that. Find the dimensions of the box that will minimize the material costs. Oh, so the box is supposed to have volume equal to 1,000 square feet, or cubic feet, sorry. 1,000 cubic feet. Find the dimensions, length, width, and height of the box, which minimizes material costs. Okay. Okay, so let's take a look at this box. So open top box. Right, looks like that, and it's got a length x, a width y, and give it a height, call it z. Right, so the volume of this box, right, is supposed to be 1,000 cubic feet, and that's equal to the length times the width times the height, x, y, z. So therefore, okay, we only want two different variables in our functions. Okay, we can't use a three-variable function. We're only maximizing and minimizing two variable functions. Right, so one of the three variables will be eliminated by the given constraint. The given constraint is that the box has to be 1,000 cubic feet. Therefore, z, so we'll take variables x and y, z will be equal to 1,000 over x times y. Over x times y. All right. So our three variables now became two, because z can be written in terms of x and y. So now, what is the thing that we're trying to minimize? We're trying to minimize the surface area, essentially. Or sorry, the material cost. Okay, so the panels of the box, and the box is open top. All right, you've got the bottom, which is x times y. And then you've got two sides, x times z. And you've got two sides, y times z. Right, this stuff costs $8 a square foot. This stuff costs $5 a square foot. And this stuff costs $5 a square foot. Right, so the cost here is equal to, well, the number of square feet here is x times y. So the cost for the bottom is 8xy. Plus, the cost for these two sides is 2 times 5, which is 10xz. Plus 2 times 5, which is 10yz. right? So the cost is equal to 8xy plus 10z times x plus y. So the cost in terms of x and y is equal to, well, z, what was z? Z was 1,000 over x times y. So here we get 10,000 over xy times x plus y. So there's the cost as a two-variable function. The cost as a two-variable function, which we wish to minimize. Okay, so the minimum value is going to occur at either a relative max or a relative min. So we're going to find all the critical points for this function here. Okay, and we're going to look at those critical points and determine which one is the max, which one is the min. And in actuality, what we're going to find is that there's only one critical point, and therefore that has to be where the extreme value occurs. It has to be a relative minimum, because that's the way the problem is defined. Okay, so let's take partial derivatives. Partial derivative with respect to x is 8y plus 10,000. Okay, so this is, let me rewrite this. X plus y over xy. 10,000, and then the derivative of this with regard to x, the derivative of the top is 1 times the bottom, minus the derivative of the bottom, which is y, all over the bottom squared, which looks like that. So cx is equal to, let's simplify, 10,000 xy minus xy, so it's minus y squared over x squared y squared. Or no, x plus y squared. No, that's xy squared. X plus y, right. Derivative of the top times the derivative of the bottom times the top, right? So these cancel. So you get cx is equal to 8y minus 10,000 over x squared, similar to that function we had before. And we're going to set that equal to 0. Right? And we're finding critical points. The partial derivative with respect to y is equal to 8x, and then it's just going to be very similar to that, 10,000 over y squared. And we set that equal to 0. So this tells us that x is equal to 10,000 over 8. So that's 5,000, 2,500. So 1,250 over y squared. And now we take this and plug that into here. Plug into cx equal to 0. So we have 8y minus 10,000 over x squared, which is 1,250 over y squared squared. So, and that equals 0. So 8y minus, and what do we have here? Well, 10,000 over 1250 squared y to the fourth is equal to 0. So y times 8 minus 10,000 over 1250 squared y to the third equals 0. So this says y is equal to 0, or y to the third is equal to 8 times 1250 squared over 10,000. Well, we can't have y equal to 0. Or there is no box. Right, a box has got to have length, width, and height. Right, so y is going to be equal to approximately, let's just figure it out, 8 times 1250 squared over 10,000. That doesn't seem right. Oh, third root of that, that's right. .772 feet. So y is equal to 8 times 1250 squared over 10,000 to the 1/3 power. So y is approximately equal to 10.772 feet. All right, given that y is approximately 10.772 feet, we plug it back into this, and we'll get only one answer. So 8x minus 10,000 over 10.772 squared equals 0. So x is equal to 10,000 over 8 times 10.772 squared. Divided by 8 times 10. Did I forget something? $10,000 over 8 times 10 point, oh, that's a comma. Right, 10.772. Feet as well. Right, so it turns out to be a box with a square bottom. Now, what is the height, z? Z is equal to 10,000 over x times y, which is 10,000 over 10.772 squared, which is equal to, so 10,000, so just get rid of the 8 there. Z was 10,000, or 1,000. 8.618 feet. So that's the dimensions of the box. That minimizes the material costs. So let's draw a picture just in summary. So this is 10.772, 10.772, and this has got to be a little bit bigger than that. I'll draw a better picture. So the bottom of the box is a square, and the height of the box is almost the same. It's nearly a cube, but not quite. Ten 10.772, 10.772, 8.618. Okay, so let's recap there. We have a rectangular box with an open top is to be made from sheets of two kinds of steel. Steel on the bottom costs $8 a square foot. Steel on the sides costing $5 a square foot. I'm going to weld it together and make the box. And the box must have a volume of 1,000 cubic feet. Find the dimensions, length, width, and height of the box, which minimizes the material cost. All right. So here's the box, length 8, width y, or length x, width y, height z. Okay, but we're only dealing with two variable functions. In Calc 1, it was only single variable functions. Here, just two variables. It can be done with three variables, but it gets a lot more complicated. So at any rate, we have to eliminate one of the variables. So 1,000 square feet is the volume of the box. That's the constraint on this problem. So z can be written in terms of x and y as 1,000 over xy. All right, let's look at the panels of the box. We've got the bottom panel and the four side panels. XZ, XY on the bottom, XZ on two of the sides, front and back, left and right sides, Y by Z. So this is $8 a square foot, $5 and $5 a square foot. So 8 times XY plus 10XZ, because there's two of them, plus 10YZ. So 8XY plus 10Z times X plus Y. But Z is 1,000 over X times Y. So there's the cost in terms of just X and Y. And then find the critical points. All right, oh, I didn't mention it. There's only one critical point. And so the minimum occurs here. There's only one critical point, and so the minimum occurs here at x and y equal to 10.772, 10.772. Now, the final bit of the question is, what is z? What is the height of that box? Oh, that was down here. So we got one answer for y and one answer for z. And so you only get one critical point. Right, in finding the critical point, right, we set the derivatives equal to 0, partial derivatives equal to 0, and we got a couple equations. And then we came down here to solve that equation. Right, so here we have y is equal to 0, or y to the third is equal to this. Whatever you pick for your solution needs to make sense for your critical point. You can't have y equal to 0, otherwise there's no box. right? The length, width, and the height all have to be positive. So it's just the cube root of whatever this big number is. Right, so we just estimated that, 10.772, and then plug that value for y back in for x into an equation to get x, and we get x is 10.772, and then that's the only critical point. So that must be where the minimum material cost occurs. And then to answer the question, we found the height, 8.618 feet squared, or feet in height. All right. How long have we gone here? 45 minutes. Tell you what, let's stop this video here and then make another one for part 2.